Kurt, I think you're muted.
I heard on NPR that someone recently gave a math talk for an entire hour on mute. But I didn't hear it myself, so I'm curious if anyone heard that or knows who the mathematician was. Anyway, thank you for keeping it from being me. So this week we're coming to the heart of the course, which is harmonic functions. In some sense, conformal mappings will serve for us as a tool for studying harmonic functions. And although I'll talk about harmonic functions in Rn, the properties for R2 are very special because of the fact that we have so many conformal maps. Before I do that, let me just draw your attention to two things. One is that the homework for next Tuesday is already posted. So I encourage you to start looking at it now rather than the Monday night, and to again always take advantage of my office hours, section, Carl's office hours, and your colleagues. All work on the homework is certainly supposed to be and encouraged to be collaborative. And the other thing I want to mention, and I won't take time out to bring this up on the screen, but last time we talked about the triply punctured sphere. The Riemann sphere was 0, 1, and infinity removed. And one of the main properties of this space is that its fundamental group is quite complicated compared to the simply connected regions we've been dealing with. And as a consequence, if you pick some homotopy class in pi1, it usually is represented by a unique hyperbolic geodesic. And these geodesics can be quite complicated. And if you look at on the course homepage, you'll find some pictures like this one, where I've actually drawn some hyperbolic geodesics in the complement of 3 points. This was, of course, accomplished by using the explicit representation of the universal cover that I mentioned last time, coming from elliptic functions. Okay, so let's turn to harmonic functions. So I'm going to start out working on Rn. And let's suppose we have two reasonably smooth functions. So we call them phi1 and phi2, real valued. Then we have the usual L2 inner product, which is the integral over Rn of phi1 of x, phi2 of x, dx1 up to dxn. And I'll abbreviate this volume form just by dx. And of course, the inner product of phi1 with itself is the L2 norm. So this space, I'm a little bit vague for the moment about how smooth I want these functions to be. If you take the metric completion of the smooth functions in this norm, you get the space L2 of Rn. Okay, now, what is the Laplacian? The Laplacian is an operator that we all know well. It's defined by the Laplacian of phi, let's say where phi is in C2 of Rn. So it has two derivatives and they're continuous. The Laplacian is defined by taking the second derivative of phi with respect to the ith coordinate, and then summing goes from 1 to n. Another nice way to think of the Laplacian is you form the whole matrix of derivatives, second derivatives of the function phi, and then you take the trace of this matrix. And a function phi is harmonic if the Laplacian of phi is equal to 0. Now, in many courses, one would then just plunge into the study of harmonic functions, but I think that begs the question, why do we care about harmonic functions? Or is it just magic that we happen to think of this differential operator and then all these beautiful properties emerge? So we'll see two answers to that in this course. One answer will relate the Laplacian to random processes, but that will take some time to prepare for. I'm going to start with the analytic approach, which explains where the Laplacian comes from in terms of not the Laplacian, but a very natural thing you can do with the first derivatives of a function. And this is really, to my mind, the motivation for the Laplacian is the following idea. Suppose you have a compactly supported smooth function, phi. So I'll say it's in C2 of Rn, and I'll put a little c to denote the fact that it vanishes outside a compact set. We can then define what's called the Dirichlet energy of this function, which measures how much the function oscillates. And this energy is given by taking the integral of the absolute value of the gradient of v squared with respect to the natural volume form. Now, what's the relationship between the Dirichlet energy and the Laplacian? Well, this Dirichlet energy is it's a quadratic form. Let's not worry about technical details of smoothness, just think of it algebraically. It actually is subservient to an inner product that's defined for two functions by taking the dot product of their gradients. But as you can see, it measures the L2 norm of the size of the oscillations of phi. But when you have two inner products on the same space, you can try to express one in terms of the other. And they are related by a self-adjoint operator. And that's what the Laplacian is. The Laplacian allows us to express the Dirichlet energy in terms of the L2 norm. And that expression is simply this. If we integrate by parts, you see this is nothing more than the integral of the sum of d phi dxi times d phi dxi all dx. And if we integrate by parts with respect to each coordinate, that allows us to take, since phi is compactly supported, it allows us to take this derivative and move it over to this side. So we just get phi times the second derivative of phi with respect to xi. Of course, a minus sign comes in. And what we get is minus the integral of phi times the Laplacian of phi dx. In other words, we get the inner product between phi and its Laplacian with a minus sign. And what that shows is that the Laplacian is the self-adjoint operator that relates the two quadratic forms, the norm of phi 2 in L2 and the Dirichlet energy of phi. Put a square there. So that's where it comes from. And then what is the meaning of harmonic? The idea of a harmonic function is that it's energy minimizing. So that it's trying its best to make this quantity small. Now what I mean formally by that is that if you take a function that's harmonic and you try to change it locally by another smooth function, then its Dirichlet energy is stationary. That is, it's like you're at a critical point of the Dirichlet energy. So these functions are the functions that are formally energy minimizing. And by formally, I mean, I'm not making any precise statement about them actually achieving a minimum and so on, because that would require quite a bit of technicalities. But the thing to understand is where Laplace's equation comes from. And the statement is that if phi is in, say, C2 of a region omega, and C is a compactly supported function on this region, and phi is harmonic, then this is in fact equivalent to the statement that if we take phi and we perturb it by adding a little bit of a new function c to it, that this derivative is equal to 0. So think about the case of a geodesic, or by comparison. For a curve to be a geodesic, it doesn't necessarily have to minimize length, say in a tomotopy class. The equator on the sphere can be shrunk by shrinking it towards the North Pole. Nevertheless, it's a geodesic. What a geodesic means is that if you take this path and you perturb it slightly, like this, you change it by adding a small normal perturbation, then its length doesn't change to first order. It might go down, in fact. If you take the equator and you push it towards the North Pole, in fact, the length does shrink, but it's stationary to first order. And similarly, these are also stationary to first order. That's what this equation says. And here's the reason. What is this derivative? Well, if you just look at what, expand out this quadratic form, what you'll find is that this is given by the integral of the gradient of phi dot the gradient of c dx. That's the first derivative of the Dirichlet energy in the direction c. And again, since c is compactly supported, we can integrate by parts and find that this is minus the Laplacian of phi times c. So to say this is equal to 0, certainly if the Laplacian is 0, this is equal to 0. But conversely, if all of these perturbations are equal to 0, then the Laplacian integrates to 0 against every smooth function. And the only function that integrates to 0 against any compactly supported function is the 0 function. So this is equivalent definition of what it means to be harmonic. Okay, so that's one motivation, is the Dirichlet energy. The second motivation, which is in fact very similar, is, let me say it's related to flux and charge. In other words, physics. And I personally think in terms of the physics of electrical fields, although you could think in terms of the physics of fluid flow, if you prefer. Another way to think about the condition of being harmonic is the following. Well, the Laplacian of phi, to go back to good old calculus class, is the same thing as the divergence of the gradient of phi. And so for this to equal to 0 is equivalent to saying that the gradient of phi generates a volume preserving flow. So Laplacians are closely related to these flows. Now, what's the meaning of the Laplacian in terms of electrostatics? In electrostatics, phi corresponds to the electrical potential of a charge distribution. And the Laplacian of phi tells you what that charge distribution is. In fact, it's often useful to think of the Laplacian as a measure by multiplying this function times the volume form. So this measure, Laplacian of phi times dx, let me call this mu, is in physics equal to your charge distribution, or your charge density, if you like, if you think of it as a function. And then the gradient of phi, or some physicists will ask that we say minus the gradient of phi, but to avoid minus signs, I'll stick with the gradient of phi, corresponds to the force field. produced by this charge. In other words, at every point, it tells you the direction in which a unit positive charge placed at that point would be accelerated under the influence of the nearby charge densities. And then phi itself is the potential. Yeah, I already wrote that down. It's the potential for this field. So that's why you might want to put a minus sign here. A charge wants to move to decrease its energy, so it wants to flow to where the potential energy is less, at which, and in doing so, it will acquire kinetic energy. Okay, but this is a very powerful idea, which we will use frequently, that the Laplacian of a function should naturally be thought of as a measure, and this measure can be interpreted as a charge density. Now, that leads to the following important idea, which we can express purely mathematically. Even though this electrical intuition is always at hand and available, suppose we have a region omega, and we have some charge inside of it, mu. How can we figure out how much charge there is inside of omega by only looking at the boundary of omega? Well, what we can do is we can look at the gradient of the associated potential phi. So we'll close the Laplacian of phi as mu. And we can look at what the net flow is through the boundary of the region. This is called the flux of this vector field through the boundary of the region omega. So the flux of the gradient of phi through the boundary of omega is the integral over the boundary of omega of the Laplacian of phi dot the unit normal vector to the boundary. So that's measuring the component of the vector field pointing orthogonal to the boundary times the surface area measure on the boundary. Okay, now what does Stoke's theorem tell us? It tells us that in general, the flux through the boundary of omega is just the sum of the fluxes through all the tiny boxes that you could use to tile omega. And the flux through an infinitesimal box is just the divergence. That's the intuition of Stoke's theorem. So by Stoke's theorem, this is equal to the integral over omega itself of the divergence of our vector field with respect to volume. And the divergence is nothing more than the Laplacian. And as long as we incorporate, this is the integral of the Laplacian dx, which is what I call mu. So in other words, it's the integral over omega of this measure mu. So it's the total charge attached to the region omega. Okay, so in short, the flux of the gradient through the boundary is the amount of charge contained in the interior. That's the intuition of coming from electrostatics, is that if you had even just a point charge inside of this region, you could detect it by the fact that there is a net positive outflow of electrical field that originates in this region, and it flows out in a volume preserving way to create a net outflux through the boundary. And between a small neighborhood, the boundary of a small neighborhood of this point charge and the outer boundary, the flow is volume preserving. So the flux through this small neighborhood is the same as the flux through the outer boundary. And the flux through the small neighborhood is just telling you the charge inside. Okay. So these are two intuitions that underlie our study of the harmonic functions, but also we'll be interested in not just harmonic functions, but functions which are close to being harmonic, but maybe fail to be harmonic on the boundary of a region or at a finite set of points inside. And this is all works perfectly well in Rn. It has nothing to do with complex analysis yet. Okay, so now we come to one of the main properties of harmonic functions. And this is really what makes the theory work. It's called the mean value property, or the most valuable player, the MVP. And what this says is it tells you how the values of a harmonic function on the boundary of a region determine the value at the center of that region, at least when the region is a ball. So there's versions for regions of different shape, but the most important one, and the one we'll use over again, is the version for a ball. So let's suppose that our function is as harmonic in our region. We don't have any charge at all in the plane or in the region that we're looking at. So suppose the Laplacian of V is equal to 0. And now we look at the average over a sphere centered at a point P of radius r of the value of our function phi of x. Let me call that A of r. Of course, it depends on the point P also, but A of PR. Okay, so we take a point and we take a ball of radius r, and we average the values of the function. Now, suppose we change the value of r. So we increase the radius of the circle of the sphere from r to r plus delta r. How does the average change? Well, basically, at each point in the region, the value of phi at the corresponding point on the largest sphere changes. And how does it change? It changes by the derivative of phi in the direction normal to the inner sphere. So the derivative with respect to r of this average function is up to a constant, depending on the radius, simply the flux of the gradient of phi through the sphere of radius r. Oh, but our function is harmonic throughout this ball. So the flux through any sphere or any closed region, the boundary of any closed region, is 0. So that says when you take the average values of the function over the sphere of radius r, the answer is constant. Okay, so the flux 0 condition implies the average over spheres remains constant as the spheres increase because its derivative is measured by the flux. But if our function is continuous, and we're actually assuming it's C2, then as the radius goes to 0, we're taking the average of a function that's almost exactly the same as phi of p. And so this function is equal to what we might call AP of 0, which is the value of phi of p. So the value of phi at the center of the ball is the same as its average over the sphere of radius r. That's the mean value property. So let me write that down somewhere where it won't disappear. So it's closely related to this flux property. Theorem. If phi is harmonic, this implies phi of p is equal to the average of phi over the sphere centered at p of any fixed radius r. Okay, so what are some corollaries of this, this condition? So one corollary it's used all the time is the maximum principle. So suppose omega bar is a compact region in Rn. Phi is harmonic on omega and continuous on omega bar. Then the maximum over omega bar of phi is actually equal to, this is finite by compactness, is actually equal to the maximum over the boundary of omega of phi of x. Now, let's put this corollary somewhat differently. You see, what this is saying is that the maximum value of phi must be achieved on its boundary. Its boundary can sense what the maximum is, and its maximum there is the same as the maximum in the interior. So in fact, a slightly stronger statement holds, which is that and this does not require any compactness, it's a local statement, a harmonic function on a, well, it's almost local, on let me say it locally. A harmonic function does not achieve its maximum in any region omega unless it is locally constant. Okay. So let's first prove the corollary. So the corollary says something very bad would happen if phi of p were the same as the maximum over omega of phi of x. Why would that be bad or unusual? Well, remember that the value at p is the same as the average over the sphere radius r. So if this maximum is m and the value at p is equal to m, then the average of the function over the sphere of radius r is also equal to m whenever that sphere is contained in our region. But for the average, this function is everywhere bounded by m. So for its average to be m, the function must be identically equal to m. So that shows that phi must be identically equal to m on the boundary of the sphere of radius r for any r that's contained in the region. So that says phi is identically equal to m on a neighborhood of p. In other words, phi is constant. So the general picture you should have of a harmonic function is not this. It should have a sort of a saddle shape near every point. This is what you should imagine the graph of phi looking like. This is phi as a function of x. It has a value at some point p, and then nearby, it should be both bigger and smaller than p, but its value should average out to give the value at p. If it were, if this weren't, so this, of course, this maximum principle also holds for the minimum of the function. So nearby, it must be above and below the values at p, unless, of course, it happens to be identically constant. And I'll remind you that if omega is connected, then a locally constant function is just constant. Okay, so let's apply that to this case. If the function is constant, then of course you get the same maximum on the boundary of the region as in the interior. And if the function is not constant, then the value at any interior point is strictly less than the value nearby, and therefore strictly less than the value at the boundary. So the maximum is only achieved on the boundary when phi is not constant. That's the maximum principle. So this is reminiscent of what happens for complex analytic functions, right? The values on the boundary of a region exert tremendous control on the values in the interior of the region. And in fact, there are many parallels between harmonic functions on Rn and analytic functions. In that sense, they all come under the general heading of ellipticity. But rather than developing the general elliptic theory, we want to examine what it looks like in this special case and then ultimately in the complex plane. So let me write another corollary down, which I'll call another theme down, which I'll call Lyell's lemma. So let's start with what I like to call the converse mean value property. So the converse mean value property says the following. It says that suppose P is locally integrable on a region omega contingent Rn, and it satisfies the conclusion of the mean value property. In other words, phi of P is equal to the average over the sphere of radius r when r is small enough. Then phi is in fact a C infinity function, and of course the Laplacian of phi is equal to 0. So notice that in particular, we have shown that the Laplacian of phi equals 0, say where phi is C2. This implies the mean value property. But now we're going to see that the mean value property implies that phi is C infinity. And so a small degree of regularity gives us a much larger degree of regularity. And in fact, this argument will also show that the maximum of phi on a region controls all of its derivatives on a slightly smaller region. Well, we'll come to that. So let's first think about this converse. So the converse applies to very rough functions. You can have a function that's discontinuous, even unbounded. But now if you suppose it satisfies the mean value property, then it's automatically smooth and harmonic. And notice that this is more or less optimal, because even to define the mean value property, we have to be able to compute the average of phi, which means we have to be able to form the average locally. And I should also say that since we're going to allow this function to be just measurable, rather than taking the average over the sphere of radius r, I'm going to take the average over the ball of radius r. Centered at P. Because a priori, a locally integrable function doesn't even have values on sets of measure 0 like spheres, although it does on almost every sphere. Okay, so let's see how you go back from the mean value property to smoothness and harmonicity. So the proof is very beautiful and simple. It works like this. So let CR be a C infinity compactly supported function on the ball around the origin of radius r, such that the integral of C of r dx is equal to 1. You might think of this function concretely as something like a Gaussian. And I'm also going to require, and this is key, that this function is radially symmetric. So C of r of x depends only on the absolute value of x, the length of x, the distance from the origin. Okay, so it's constant on every sphere. And now suppose phi satisfies the mean value property. Then let's think about what the convolution of phi with C of r is. So first, maybe I should remind you what the convolution of two functions is. The convolution of phi with C of r at a point x is the integral over all of Rn of phi of x times phi of y, C of x minus y dy. So we take these two functions and we slide them across one another, and we average the values of phi with our bump function, but now centered at x. So in other words, the value at x is obtained by taking our bump function, translating it so it's centered at the point x, taking our integrable function phi, multiplying it by this bump function, and then integrating. Now what you see is that this bump function can be thought of as a convex combination of averages over balls. And since the average over a ball is equal to the value at the center of the ball, this weighted average over balls is also equal to the value at the center. So this is just equal to phi of x by the mean value property. On the other hand, convolution with a smooth function is a standard way of taking a locally integrable function and approximating it by a smooth function. So this function is actually smooth. So let me remind you that if you take the, we sometimes use the notation d alpha to take the derivative of a function. This means alpha is a multi-index of integers, alpha 1 up to alpha n. And this means you take the alpha 1 derivative of x1, the alpha 2 derivative of x2, etc., the alpha n derivative of xn, just a compact way of expressing many derivatives. If you take the alpha derivative of a convolution, like phi convolved with CR, this is the same as differentiating either of the functions here. For example, here, you can see x only occurs in the function c. So when we differentiate with respect to x, we can do so under the integral, and we only get the derivative of this function. And so we get the convolution of phi with another compactly supported smooth function. And since this is integrable and this is smooth, this is also locally bounded, and in fact in C infinity. So that proves that if phi has the mean value property, then this function is C infinity. Let's just say this is obviously continuous, since this is compactly supported, and since all the derivatives exist and can be nicely expressed like this even, this is a C infinity function, but it's equal to our original function. So our original function is stationary under convolution with bump functions of unit total mass, provided they're rotationally symmetric. That's an extremely striking and powerful theorem, but that's really what the mean value theorem says. It's nice to talk about it in terms of spheres or balls, but it also holds for convolution with any radially symmetric function. Convolution with the indicator function of a ball can be thought of as a generalization of this case, and that's what the usual mean value property says. Okay, so now we have that our function is C infinity. What remains is to show that a smooth function with the mean value property has to have its Laplacian equal to 0. And that's quite striking, I think, that, that when a smooth function satisfies the mean value property, it's harmonic, and thus the mean value property is equivalent to being harmonic. So we'll now show mean value property plus C infinity implies harmonic. And the way to do this is let's use Taylor series. Now that we know that our function is smooth, so we can write phi. We'll verify that the Laplacian of phi at 0 is equal to 0 when it satisfies the mean value property. Of course, the same argument will work near any point because it's a translation invariant condition. So what is phi of x equal? for x near 0. By Taylor's theorem, this is equal to the value of phi of 0 plus a linear term, which is, let me just write it as the sum of ai times xi. Of course, these ai's are really the gradient of phi. But all I care about is that I'm approximating this by a linear polynomial, a polynomial homogeneous of degree 1. And then the next term is the sum of a homogeneous polynomial of degree 2, a linear combination of the products of the coordinates. And then the next term is on the order of the absolute value of x cubed. Now let's think about the mean value theorem. Because of the fact that each term is negligible with respect to the rest, we must have that the average of each term is compatible with the mean value theorem. So the average over a small ball of this term, by assumption, is equal to phi of 0. And the average of this function is also equal to phi of 0. So that means that the average of this function over a small ball had better be equal to 0 so that it doesn't mess up this average. And indeed it is. If you take any linear function on the ball, it's an odd function. If you change x to minus x, it changes sign. So its average over a ball has to be equal to 0. So that's true. And therefore, the next order term must also average to 0 over a ball. Now, let's look at these products, xi times xj. So if I is not equal to j, then xi, xj is odd under changing xi to minus xi. And so the off-diagonal terms here average to 0 over the ball. But what about the on-diagonal terms? That's the real problem. What we must have is that the average over a ball of the sum of bii times xi squared is equal to 0 for the mean value theorem to hold. But the average of one of these coordinates is the same as the average of any other coordinate squared because of the symmetry between the coordinates. So this average is just equal to a constant times the sum of the bii squared. But what is bii? Bii is, well, if we were to differentiate this function, a 2 times bii would come down. So 2 times the sum of bii's is nothing more than the Laplacian of phi at 0. And so the sum of these bii's, sorry, these are just ordinary. The sum of the bii's is equal to the Laplacian at 0 up to a constant, so it too must vanish. And therefore, a function that satisfies the mean value property is necessarily harmonic. So this again is yet another strong and useful equivalent characterization of harmonic functions. So we've seen harmonic functions minimize Dirichlet energy. They give rise to volume preserving flows, and they satisfy the mean value property, and they can be thought of as electrical potentials. And all of these characterizations are equivalent. But this one I think is the most striking. The reason being, it doesn't assume any differentiability of the function. Okay, now, why is the mean value property arguably better than the usual definition of being harmonic, the Laplacian vanishing? Let me remind you of one of the beautiful theorems in complex analysis. If you have a sequence of analytic functions that converge uniformly, their limit is, of course, continuous, because a uniform limit of continuous functions is continuous, but their limit is actually analytic. And in fact, all the derivatives converge. And this is also true for harmonic functions. So let me just start by just stating the most important of these principles, which we'll use over and over again. Let Vn, let's say in the continuous functions on the domain omega, be harmonic. And suppose Vn tends to phi in the continuous functions on omega locally uniformly, or let's say uniformly on compact sets. That's the usual notion of convergence that we use when we have an open domain. We don't require quite uniform convergence. The original function doesn't have to be bounded, but when you look on any compact set, you see a uniformly converging sequence of harmonic functions, then phi is harmonic. So what's the proof? The proof is simply that if you take the value of phi at a given point p, this is equal to the limit of the values of these functions at the point p. But these functions satisfy the mean value theorem. So this is equal to the limit of the average over a suitable ball centered at p of the functions phi n. And since the functions phi n converge uniformly, the average converges uniformly. So this is equal to the average over the ball b of the function phi. And so phi has the mean value property, and therefore it's harmonic. This is a little bit like using Morera's theorem to characterize analytic functions. The mean value property is very robust. In particular, it's preserved under uniform convergence, and so being harmonic is also preserved. Now, there's a caveat which will be implicit in the next proof that I'm about to give. Let me just say it for the moment. Also, once you have uniform convergence on compact sets, the alpha derivative of Pn tends to the alpha derivative of phi uniformly on compact sets. So not only do the functions converge, but all of their derivatives converge uniformly. Now let's see where this caveat comes from. It's implicit in the proof of the following theorem, which is equally useful. So let's consider harmonic functions on a domain, or let's say for concreteness on a ball, and suppose that they are uniformly bounded. Now, if we had uniformly bounded analytic functions, then every sequence would have a convergent subsequence. And in fact, the same thing is true for harmonic functions. So let's call it H contained in the continuous functions on a domain omega be the set of harmonic functions such that the sup over omega of the absolute value of phi is less than or equal to some constant m. So I'll put m in here. Harmonic functions that are uniformly bounded by a constant m, then phi is, then hm is compact in the usual topology, in the topology of uniform convergence on compact sets. So you'll remember we proved a theorem like this in our review of complex analysis. If you have analytic functions that are bounded on a domain, then any sequence has a subsequence that converges uniformly on compact sets. And the same thing is true for harmonic functions. So let's see why. Well, this is very nice. So remember that to prove a sequence of continuous functions has a uniformly convergent subsequence. And once we do that, we can apply this theorem. To prove we have a uniformly convergent subsequence, we just need to show there's a uniform bound on the derivative of these functions. And in fact, this is true for any derivatives. So let's, for the proof, we fix a small r greater than 0, and we let kr be the set of points x and omega, such that the distance from x to the boundary of omega is greater than r. And let's say also the absolute value of x is less than or equal to 1 over r, just to ensure that this is compact. So here's our region omega, and then we find within it some region k of r. It doesn't get too close to the boundary and is itself bounded. And we note that omega itself is the union of these krs over r greater than 0. Well, all we have to do is show that the derivatives of phi are bounded on this set. We will show that d alpha of phi in absolute value is uniformly bounded on kr. In fact, it suffices to show the first derivatives are bounded because that gives a uniform modulus of continuity, and then we have a uniformly convergent subsequence. But this is easy. But the absolute value of d alpha of phi, well, on k of r, and of course, this is for all p in Hm. So the absolute value of the derivative at a point p, if p is in kr, the derivative at this point can be expressed as the convolution of phi with the alpha derivative of the bump function we've chosen for radius r. And therefore, the absolute value of d alpha phi is less than or equal to the sup norm of phi times the L1 norm of this function here. So if this is less than or equal to m, it's less than or equal to the product of the L1 norm. So it's less than or equal to the sup norm here times the L1 norm here. So times the suitable norm of the alpha CR. So you're taking a bounded function and convolving it with some fixed function, then the result is still uniformly bounded. The constant depends on the thing you're convolving with. But the important point is that the bound depends on r because we had to choose a bump function that had small support. So its derivatives may be quite large, but they only depend on r. And r is fixed when we're on k of r. So this is equal to a constant m sub r. And this is uniform on kr. Therefore, the Arzela-Scully theorem applies. We have a uniformly convergent subsequence, and uniform limits of harmonic functions are harmonic. Okay, now in the process, we proved more. What we proved was that if you have a function that's bounded on a given region, then all of its derivatives are uniformly bounded on compact subsets of that region. So let me just write this as a corollary that the sup over omega of the absolute value of phi controls, that is, gives a bound for the sup over each kr of the absolute value of d alpha phi for all fixed alpha and r. Which means this quantity is bounded by a multiple of this quantity where the constant depends on alpha and r. Okay, so these are tremendous strong properties enjoyed by harmonic functions. Compactness, automatic smoothness, and persistence under uniform limits. Now, for later use, I just want to mention a modification of the mean value property that's very important. And its importance will only gradually become clear, but I'll say one of the reasons why it's important. So this is the notion of a sub-harmonic function. So a sub-harmonic function does not have the automatic smoothness properties of a smooth one, but nevertheless, it satisfies a modified version of the mean value property. So the definition is if phi is C2, then we say that this function is subharmonic if the Laplacian of phi is positive, or at least non-negative. So we don't require that phi vanish, the Laplacian vanish, but we require that it has a definite sign. So if you like, these correspond to the potentials of positive charge distributions. And an easy fact is that if phi is subharmonic, then it satisfies a sub-mean value property. Namely, the value of phi of p is less than or equal to the average over b of phi of x for any ball b, any symmetric ball b centered at the point p. You just apply the same proof, except now what we have is, since there's possibly positive charge for this region, the flux through a boundary of a region increases as the size of the region increases. That means that the average over a sphere can increase as the radius of the sphere increases. And so we only get an inequality. The value of phi in the middle is bounded by the values on the boundary. Oh, but this inequality is all we need to prove the maximum principle. So a corollary is sub-harmonic functions satisfy the maximum principle. On the other hand, they do not satisfy the minimum principle, which harmonic functions do. That is, the minimum is not necessarily achieved on the boundary. And of course, there's a symmetric kind of function where the Laplacian of phi is less than or equal to 0, and these are called super harmonic functions. Now, how do you gain some intuition for subharmonic functions? Well, the first thing to think about is, what is a subharmonic function? What is a harmonic function on the real line?
Linear function.
Thank you. So here's a harmonic function on R. So this is the case n is equal to 1. What is a subharmonic function on the real line? Someone else.
It's a concave function.
Almost.
It's curving up, whichever one that means.
Okay, it's a convex function. Thank you. So this is subharmonic. It's a convex function. And I've drawn it as if it were smooth, but of course a convex function can also have corners. And so the second derivative should be positive, and the function should be convex. But what you'll notice is that the harmonic function is beautifully smooth. In fact, it's linear. The convex function doesn't have to be C2. This function has a piecewise constant derivative, but the derivative is increasing. That's the key point of a convex function. And the second derivative is, in this case, a sum of, it's an atomic measure supported at the points where the function takes bands, at least if we think of the second derivative as a distribution. So if one wants to deal with subharmonic functions that are more general than C2 functions, then the intuition is that the Laplacian of phi should be a non-negative measure, rather than just a positive function. So we could require instead that the Laplacian of phi is a non-negative measure. Or we could require that phi is locally integrable and it satisfies this subharmonic condition. And in both cases, we get the same class of functions. Now, sometimes it's nice to allow a subharmonic function to assume the value minus infinity. And that's fine because if you go to the place where the function is minus infinity, that's certainly going to be less than or equal to the average over the boundary. So we occasionally allow for subharmonic functions phi of p to be equal to minus infinity. And one of the reasons for doing this, and this is just to look ahead for a second, is that it will turn out that if f of z is analytic on a region omega contained in C, then this implies log f of z, the real part of the logarithm of f of z, at least if we form a unique branch locally, is subharmonic. Now you might say, wait a second, the real part of an analytic function is harmonic, isn't it? And indeed it is, except that the logarithm might not be defined. It's not defined when f happens to have zeros. So in fact, it's harmonic if f has no zeros. And this is a powerful tool that we'll use to control analytic functions in terms of harmonic functions. But if we have a zero, what we get is a function that looks locally like something like the logarithm of the absolute value of z. In other words, we get a function which is up to adding a harmonic function, has a singularity which goes to minus infinity. And this, at every other point, the function is analytic in the ordinary sense, as a harmonic in the ordinary sense. And so this actually is admitted as a subharmonic function. And it won't satisfy the mean value property. It will only have this inequality if we take the average over the log of the function over a point p, and if x happens to have zeros inside. So we'll come to that, but this is one of the main motivations for even discussing subharmonic functions, is they arise very naturally from analytic functions. Okay, so any questions on the Laplacian in Rn? Okay, so now let's go to the world of complex analysis, which I've already hinted at with this foreshadowing of how we relate analytic and harmonic functions. So the Laplacian on the complex plane, which we think of as being isomorphic to R2. Our coordinate z being x plus I1. Okay, so here's the main point about analysis of the Laplacian in the complex plane. The Laplacian of a function is conformally natural. So one way you know that something should be relate nice with complex analysis and harmonic functions is that if you take a harmonic function and you compose with an analytic function, then the result is still harmonic. So being harmonic is invariant under change of coordinates. Another reason you know that these two things should be related is that every harmonic function is locally the real part of an analytic function. That must be a powerful tool. And to bring these facts to the fore, what would be nice is to describe the Laplacian in a coordinate independent fashion. The way that we've written the Laplacian, if you change coordinates, the Laplacian will scale in some complicated way by the derivatives of your change of coordinates. But if you regard the Laplacian as a measure, that is, if you take the Laplacian of phi in the complex plane and multiply it by dx wedge dy, the standard area form on the plane, it turns out that this is a natural two form in the sense that it's invariant under analytic changes of coordinates. It behaves correctly under the Riemann mapping. And what we will show this is that we'll rewrite this two form as d star d of phi. And this is a conformally invariant way of expressing the Laplacian. But the value of the Laplacian of a function is now no longer a function, it's a two form. But that two form in local coordinates is the ordinary Laplacian times the ordinary area form. And finally, we'll turn out that there are natural operators similar to the exterior derivative called d and d bar. If we take the d bar derivative of phi and then apply the d derivative, we'll again get a two form, and up to a factor of 2i, this will be the same as the conformally natural Laplacian. So in the complex domain, there are three ways of getting to the Laplacian. And these two are expressed in such a way that they're conformally natural. Okay, so let me explain in turn what each of these two expressions means. So first, what is the Hodge star? This is an algebraic operator on one forms in C or on any Riemann surface. And in local coordinates, where z is x plus iy, is defined like this. You take the star of dx and you turn it into dy, and the star of dy is turned into minus dx. So this is how it acts on the cotangent space at a point. And you'll notice that if you do the star operator twice, you get minus 1. So it's sort of like a multiplication by I. And if you think of your space of one forms as being spanned by dx and dy, then you can see what the star operator does is it rotates dx over to dy, and it rotates dy over to minus dx. And the square of that 180-degree rotation, of that 90-degree rotation, is a 180-degree rotation. Now, the main point about this star operator is it only depends on having a complex structure on the tangent space. In other words, it's essentially the same as knowing what j is on the tangent space. In fact, it's dual to the operator j, which rotates tangent vectors by 90 degrees. So this operator is intrinsic to any one-dimensional complex manifold. And of course, the d operator, the de Rham exterior derivative, is also intrinsic. And that shows that this formulation of the Laplacian is coordinate independent on any Riemann surface. And just to make that precise, let me just write down the property that this has, which is that if we have, say, a conformal isomorphism between two domains, and we have a function phi over here, then we could form d star d of phi composed with f. In other words, pull the function phi back to this domain and then form its Laplacian there. And that's the same thing as pulling back the Laplacian of phi on this domain and forming the Laplacian here and then pulling it back. Okay, so let's see why these two things are the same. Well, let's just work in local coordinates where we have this explicit formula for the star operator. So if we take d phi, what is this given by? So I'll use the shorthand phi x for d phi dx, similarly for phi y. So d phi is the x derivative dx plus the y derivative dy. That's the usual de Rham exterior derivative of phi. It's a one form. What's star of d phi? Well, we just have to change these dx's and dy. So this becomes dx dy minus dy dx. And now usually if we had done d times d, we would get 0. The exterior derivative squares to 0. That's why the forms form a chain complex. But because we rotated, we don't necessarily get 0. What do we get? Well, d star d phi is, so first we differentiate this guy with respect to x, and we get phi xx dx wedge dy. Okay, now we also get a term phi xy dy wedge dy, but of course that's 0 because dy wedge dy is 0. And similarly here, the cross term cancels out, and we're left with minus phi yy dy wedge dx. But if we reverse the order of these two terms, then the minus sign changes to a plus, and we can incorporate these two together, and we get indeed exactly the Laplacian phi dx wedge dy. Okay, so this Hodge formulation of the exterior derivative that gives the Laplacian in local coordinates up to the factor of this locally defined volume form. Okay, so that's one way of formulating the Laplacian using complex analysis, or rather the Hodge Star. Let me just make a comment about the Hodge Star, especially for people who might someday study gauge theory. On an n-dimensional manifold, the Hodge Star is natural on the forms of dimension n/2, the middle dimensional forms. It's conformally natural. And when you study Yang-Mills theory, on a 4-manifold, you have a bundle, you have a connection, you have its curvature, and its curvature is naturally a 2 form. And 2 is half of 4, so there's a natural notion of a harmonic 2 form, which is one which satisfies this kind of equation being equal to 0. There's also the notion of a self-dual 2 form, which is one that satisfies the property that star alpha is equal to alpha, or star alpha is equal to minus alpha. And that's in the case of a 4-manifold. Those are the Yang-Mills equations, which for the connection on a principal bundle that minimizes some sort of energy functional, which is built naturally out of, which is analogous to the Dirichlet energy. Okay, now let's look at this second equation here, dd bar. What does that mean? So let me review what the notion is of the operation of taking the derivative of a function with respect to z. So this is given by 1/2 df dx minus I df dy. And similarly, the derivative with respect to z bar is 1/2 df dx plus I df dy. Now you might wonder, why didn't I put a plus sign in here? What's this 1/2 doing there anyway? Well, these operators are set up so that first they form a basis for the tangent space, because you can write df dx and df dy as linear combination of these operators. And secondly, they have the property that if you take the z derivative of z, you get 1. But if you take the z derivative of z bar, you get 0. And similarly, the derivative of z bar is 1. The z bar derivative of z bar is 1, and its z derivative is 0. So these operators act on the space of polynomials generated by 2 variables z and z bar as if these were independent variables. The second point about these operators is that to say a smooth function does not depend on the conjugate variable z bar is exactly to say that it's analytic. So df dz bar is equal to 0 if and only if f is analytic. This is a very compact way of packaging the Cauchy-Riemann equations. And then the main thing we're going to do is we're going to use these operators to take the operator d, which sends functions to 1 forms, And we're going to express it as a pair of operators, d plus d bar, which sends functions to what are called 1-0 forms and 0-1 forms. And once we've done that, we'll be able to make sense of this 2 form and finally get yet another expression from the Laplacian that uses the complex structure on the underlying space. Okay, so we'll do that next time and then get deeper into solving the Dirichlet problem, which is really the core of the theory of harmonic functions. So I urge you to look at the course notes, and I put in many references, including I put in references to Alfor's book on basic complex analysis, which has a very good treatment of harmonic functions and the Dirichlet problem that complements what we're going to do in the course meetings. Okay.
I have a question.
Yes.
Does the fact that harmonic functions